guys, today we are going to start with yet another video, and this video is going to be about perplexity and cross-entropy. So this topic has been in using in the part of evaluation for basic ML understanding. We all know that cross-entropy plays a very important role when we are understanding the very basics of ML, that how things work and how all the backend things of probability works. So we'll start that what exactly is cross-entropy and perplexity and what is their use using some examples. Okay, so starting with the very first point, that is probability distribution, which is probability distribution. Now from the name itself, it's pretty clear that what we are going to discuss, right? That how ML models have different scores that have been assigned according to their training. Okay, so let's say I'll take an example of, let's say, a basic ML model. Okay, so how do they work at the backend? We have this particular term which is called probability distribution, right? Now what is this? It is how likely different event occurs, right? Because let's say you have multiple events and you want to figure out that what is the chance of a specific event occurring, right? So how likely different events occur. So for example, if I want to give you one example, that is going to be words in a sentence. Words in a sentence. A very simple example, that let's say I have a cat. I have a cat. Now these are 4 words, right? So now what is the probability that what is going to be the next word? Okay, let's say I have a cat which, so okay, this is going to be the next word, right? Let's say, but your model is giving you multiple options. Okay, it is giving you which, what, and when. Okay, let's say 0.1 for this, 0.6 for this, 0.3 for this, something like that. This is called as the distribution of probability in the game of words. Okay, now we need to understand some basic concepts, which is true distribution. True distribution, and let's denote with this as the symbol P. Okay, so now what exactly does this mean? It means actual or ground truth probability distribution. Okay, so this is actual or ground truth. Very simple, right? Now when I give you an example that predicting a word in a sentence, so that same example can be used here also, right? So let's say we have the probability of cat. Okay, probability of cat is equals to 0.8 here. This means there's a 80% chance that the next word is going to be cat. Okay, this is going to be the next word when I say this. Now similarly, let's say we have probability distribution of dog. Probability of dog is 0.1. So this means 10% chance that the next word is going to be dog. Okay, dog, the next word. Similarly, if let's say we have a probability distribution of bird and this is 0.18, what is this? 18% chance that the next word is going to be bird. Next word is going to be bird. So simple as that. Okay, now we have another term which we call probability distribution, predicted distribution. Okay, we have predicted distribution. Now this is not much different. Predicted distribution. Okay, this we denote, let's say, with the word Q. Okay, so we have distribution Q. So what is this? That distribution your model generates as prediction. Okay, it's how likely the model thinks each event is. How likely the model thinks each event is. The model thinks each event is. So not at all complex, right? Now after training, let's say you have trained a model. Okay, let's say this is a model M. You have trained it. Now post that the Q of cat is 0.5 and Q of dog is 0.3. Okay, so what does this mean? That the model is predicting on the basis of the next word that, okay, 50% chance the model is thinking it's going to be 50% and this dog is going to be 30%. So what is our goal in this? What is our goal? What is our goal in this? So our goal is simple as that. We need to bring Q closer to P. This is our goal, right? We need to bring Q closer to P. Now I think we have understood majority part that what is probability distribution, right? So I think let's move to the next page. That is going to be cross-entropy. Okay, cross-entropy. The word itself sounds complex, but it is very simple if we understand from what we understood on the top page. It is the difference between two probability distribution for a given set. As simple as that. Difference, right? Difference between two probability sets. Probability distribution for a given set. Cool. So what does this mean for a given set? It means that how much the Q approximates the distribution, the true distribution P, right? Q's approximates the true distribution P. Okay, we remember, right? Q is the predicted one, true distribution is P. So how are we going to calculate it? We have a simple formula for that, which is the sum of the whole, right? The Px, the true probability of an event, and the log of Qx. Now I think most of you will be thinking that why this log. I'll explain to you. So what is Px? True distribution, right? True distribution of x. Okay, and then you have the predicted probability. Okay, the predicted probability. So how complex was this? Simple as that, right? Now understanding that what does this exactly mean, this sentence. What is going to cross-entropy tell you? It is going to tell you that how surprised, the word surprise, remember this, how surprised the model is when it makes the prediction. So what is our goal in this? What is our goal in this? To minimize it, right? Minimize cross-entropy. This should be our goal, right? Because we want our model to be confident, right? We want our model to be confident. We don't want it to be, much surprised whenever making a prediction, right? So when we see y log here, why did we choose the word log, like this term log here, mathematical term? So this is to depict the surprise, or maybe you can use this word notion of information. Okay, notion of information. Okay, now the model's confidence, let's say it's C, the model confidence is C. So whenever the log obviously is going to make things smaller, so the confidence is going to be big. Okay, whenever the log is going to be small, and whenever log is going to make things bigger, the confidence is going to be reduced. So log whenever is bigger. Okay, so it's simple as that. We need to make sure that the model is confident on whatever it is saying and not at all, and not much surprise. Okay, so I think we are done with cross entropy. Next term, what is the next term? Next term is the one we were talking about from the beginning, perplexity. Perplexity. Okay, so perplexity can be defined as, metric derived from cross entropy. It's a simple metric which has been derived from cross entropy. Okay, so it is a measurement of how well a distribution of probability predicts a sample, right? So you can say it's a measure of uncertainty, right? It's a measure of uncertainty. Okay, simple as that. Because whenever we are talking about that, how well the distribution of probability predicts a sample, we are talking now that how good is the uncertainty of the model, right? So what do we want, right? The lower the perplexity, the lower, okay, I'll erase this. Yeah, so the lower the perplexity, the better is our model, obviously, right? Better is the model, because we want our model to be, as certain as possible. We don't want the model to, have a lot of uncertainty in it. So let's say perplexity of the distribution of Q, it is going to be 2H P comma Q. What is this H P comma Q? It is going to be the cross entropy, right? This word is going to be the cross entropy. So for example, let's say 2 raised to the power 3 is going to be, let's say the entropy was 3, okay, cross entropy. So the model has 8 possible outcomes, okay, 8 possible outcomes. So we don't want that, right? We want the model to be more confident and not uncertain between 8 outcomes to answer something, right? So let's say the confidence is C. So the perplexity is obviously, the lesser the perplexity, the better is going to be the confidence. And if the perplexity is high, the confidence is going to be low. So our goal is to, have a less perplexity model. So when it comes to usage for cross entropy, I think I already clarified above. Cross entropy, because as you saw, it is a difference between the distribution that we were seeing. So the usage is simple as that. It can be used as a loss function. Okay, loss function in classification tasks. Let's say, yeah, classification tasks. Okay, now when you have perplexity, what is going to be its task? It can be used as an evaluation metric. It can be used as an evaluation metric in language modeling. So even in LLMs, perplexity plays a very crucial role when it comes to evaluating how better which model is. So you compare the difference between multiple models, let's say model 1 and model 2, using this perplexity. If model 1 has lesser perplexity, is better than model 2, right? So yeah, now I think we can take one example to understand that how things are working here. So yeah, I'll take one example of the example that we were talking about previously. Let's say we'll take one example from language modeling only. Okay, predict next word in a sentence. Let's say the word is dog. Okay, dog, and the true distribution can be, let's say we can take 1. But the model, what does the model give? I'll write down what does the model give. So let's say model gives cat is equals to 0.7 and dog it gives 0.3. Okay, so what are we going to do? We are going to calculate for dog. It is going to be h p comma q. Because we don't have a true distribution for a cat, we can skip that. And this is the dog. Okay, log of q and the dog. Okay, so it's simple as that. We have 1 into log. We can take the basis 2 for here. Yeah. So we have minus 2 0.2 log. That is going to be around 0.2 is I think 2.32. Yeah, 2.32. Okay. So the perplexity is going to be 2 raised to the power 2.32. So it's going to be something around 0.21, something around that. Yeah, something around that. So what can we conclude from this? That 2.32 bits of information, right? Bits of information is required to explain the true distribution. Okay, and the 5.021 model is uncertain, as if it were to choose from 5 possible options. Okay, this is the answer. Now I'll take one more example where we have multiple let's say things. Let's say we have probability of cat is equals to 0.7, probability of dog is equals to 0.2, and let's say probability of mouse we can take mouse 0.1, and these are the predicted by our model. Okay, for the true I will take one more example. Let's say probability of cat is equals to 0.6, probability of dog is going to be 0.4, and these are the true distribution. Okay, so now we need to do the sum. This is our goal, to do the sum, right? So I'll change the color. Now probability of cat, the log of q cat. Okay, this is going to be 0.6 into log of 0.7. This is going to be 0.30, and similarly for probability of dog we can say log of q dog. Okay, so what is it? The dog is 0.2 I think. The true is 0.4, and inside the log it is going to be 0.2. Okay, so this is going to be 0.4 into 2 I think 2. Okay, cool. 0 minus 0.92. Okay, cool. So mouse we don't have to do because we don't have a true distribution for that. We can skip this mouse. Now we need to add this, right? 1 and 2. We need to add this. This was the formula, right? Adding both of them. It was the sum of, right? So the sum is going to be 0.30 minus 0.92. So this is going to be I think minus 1.22, right? And because we have this minus outside, so this will become 1.22. Cool, looks good to me. Now suppose that we are going to calculate, this was the cross entropy. Perplexity is 2 raised to the power 1.22. This is 2.37. So yeah, this is our final perplexity, and this was our cross entropy. So yeah, simple as that. I hope you guys have understood what is the purpose of perplexity and cross entropy, and how are the basic terms like probability distribution used here, and what are their usage. So yeah, thank you for watching the video, guys. Thank you and have a nice day.